Well, thank you very much, Vice-Chancellor, and thank you all for coming this evening. I hope that after the next 50 minutes, hopefully, that you will have enjoyed this topic as much as I enjoy it. Enthusiasm is certainly something I can give you in great measure. But I'm going to start somewhat unconventionally by something where an event took place the other side of the world, and somehow I'm going to relate this to solar energy. So that was the Clipper yacht race. I was told it would be a nice sail across the Pacific Ocean. It was 6,000 nautical miles of sheer terror, I would say. But the question is, there's a serious question. I was experiencing firsthand some fairly extreme weather conditions. Of course, the first time I crossed the Pacific Ocean, one of my crewmates from Jamaica Lightning Bolt, April, did the leg before me, and I think for all of us we were throwing ourselves into the deep end. But it really raised in my mind this whole question of climate change. We hear about it. There's been recent events in Australia. But how do we... Okay. So how do we look at individual events, and how do we relate that? Because the weather is a chaotic system. We know that long-term predictions are extremely difficult. And there's all sorts of methods that climatologists, meteorologists use to try and predict what's going to happen in the weather. And certainly they use these methods to backcast and say, well, that's why it happened. And they've done exactly that with the Pacific weather. And I was interested to see, well, was it exceptional? Well, indeed it was. Because during last winter, we knew that there were some fairly unusual conditions here in this country, but actually across the Northern Hemisphere. And if we go on, for the meteorologists amongst you, El Nino we've all heard of. You probably haven't heard of the Arctic Oscillation. You probably don't know what the negative Arctic Oscillation is, but in simple terms, what it meant was that the low pressure systems that normally sit well to the north in the Pacific Ocean came further south. And we were told we were not allowed to go further north than 45 degrees because there'd be some nasty storms. There were nasty storms down below 40 degrees north, and we got caught in them. Okay, so we could very easily say, well, this is climate change, and that's what caused it all. These are the weather conditions, actually, the forecast for the day which we arrived in San Francisco. Gusts 75 miles an hour, that kind of thing. It was nowhere near as bad as, well, we didn't have gusts of 75 miles an hour at that point, but we had those sorts of gusts earlier. But that storm wasn't as bad as some of the storms we'd encountered. But can we link this to climate change? Well, yes and no. Okay, there isn't a simple answer to it. And of course, this is not my subject, so I can pontificate about it and quote what other people say. Individual weather events cannot be directly related to climate change. But what we are told by the experts in climate prediction is that with warming of the ocean temperatures, we can expect a greater occurrence of extreme weather. And that's actually what we've been observing over the last decade. So let's just sort of take this theme of climate change and see what the evidence is. And it is something where I think as a body of scientists, there is pretty good agreement. I mean, there's not, amongst scientists and academics, you know, do we agree on things? Mostly not. So I would say that the degree of agreement on this is quite remarkable. But judge for yourselves, okay? These are two bits of evidence that I look at, and remember, this is not my subject. The one is, and there's various forms of graphs plotting ocean temperatures, air temperatures, and so on, going back, in this case, hundreds of years, over 1,000 years, taking evidence from glaciers and so on. And it's possible to be able to work out what temperatures were in the past, where by that little circle there, where temperatures have been increasing over the period of the Industrial Revolution. If we look at the actual carbon dioxide concentrations in the atmosphere, and I mean this can be analysed very easily, it's something that I don't think we can argue about. We're moving up towards the region of 400 parts per million. And that's a level of carbon dioxide in the atmosphere which hasn't existed for millions of years. So we are definitely in new territory. And the predictions are we've at present got something like a 0.7 degree rise in temperatures already, and we are seeing what we think is a greater occurrence of these extreme weather events. So imagine what will happen to 2 degrees. Now the objectives for all the international agreements are trying to limit it to 2 degrees. But 2 degrees itself is going to cause considerable change. That's the prediction. Okay, so what can we do to limit carbon dioxide emissions? Well, we're heavily dependent on energy from fossil fuels. That's coal, gas, and oil. And particularly in this country, as I'll show you in a moment, if I can make this work. I just have to be patient, I've been told, and it will happen. Okay, this is a website which will tells you what is being produced in this country on any particular day. So that's how much the proportion of electricity being generated from fossil fuels at the top there. The next one is nuclear, and the one down below is total renewables. That includes hydro, which we had before it became fashionable to talk about renewable energy. It includes wind, and obviously we've got lots of examples now of wind turbines, and a very tiny amount of solar. So it's only 4.5%. How many of you remember predictions around about 2000 by the government that we would achieve 10% electricity generation from renewables by 2010? As we got closer to 2010, nobody talked about that. They talked about the 2020 targets. So this is a huge challenge. Doesn't want to go away now. Right. And anybody's interested, I can give you this web address. So you can check day by day and write to your MP saying we're not doing enough. Okay, so the UK government target, one of the targets, if you like the big target, and this is part of international agreement, is to reduce carbon emissions by 80% by 2050 to limit this temperature rise to 2 degrees, which already is getting into dangerous territory. How can we achieve this? Well, moving towards a low-carbon economy, the first thing we've got to look at is what we're using our energy for. And we're not looking at just electricity, we're looking at heating, and we're looking at transport. And it's interesting, international agreements have tended to miss out things like air travel and shipping and so on. These are now being included because we've got to look at the total equation. So energy efficiency. So can we cut down, can we use more efficient technology? And there certainly are revolutions happening in, for example, lighting. In the next few years, you won't be replacing light bulbs, there'll be LED lights in your house. And there may well be EU regulations that say that no new halogen lamps and so on will be installed, because the LED lighting is a lot more efficient. Build a new generation of nuclear power stations. That's been very much on the agenda. Fusion power. This is a technology which relies on the fusion of nuclei, same process which goes on in the sun. And this could produce phenomenal amounts of energy without the problems of fission power of nuclear waste. That's what's promised, but it hasn't happened yet, and nobody knows exactly when it's going to happen. So the task is huge. We've got various forms of renewable energy, which we know about now. Some technologies which are in the demonstration phase, such as tidal energy. And we've basically got to think of using all of these if we are going to meet this target. Now, that's not the sort of thing that you hear in the news. What you hear is we've got to go for nuclear, or we've just got to have more wind turbines, or maybe we've got to wait for fusion power and then it's all going to be okay. The reality is that we need all of these. And that creates actually a very complex market. So let's look at the potential for solar radiation. It's very small in this country. Globally, it's less than 1% at present in terms of the amount of electricity that's generated from solar. So the first thing you've got to look at is, has it got the potential? Well, the potential is absolutely enormous, as indicated there, that just in one day there's more than enough energy to supply the whole population of the Earth for 27 years. Of course, we're not saying that we're going to capture anything like that amount. We only have to capture a tiny amount, and we can supply a substantial amount of our energy needs. And of course, I like to give the example in Wales, because I'm asked, why are you doing solar energy research in Wales when it rains all the time? Well, we've done calculations, and just 1 square kilometre, this is the total solar radiation falling on 1 square kilometre in the year. That would generate 10% of our electricity needs within Wales. So we're not talking about marginal amounts. We're talking about it would not be difficult, even with today's technology, to generate 10 to 20%. Remember those figures from nuclear? Currently, about 19%. So it can be very substantial. Okay, let's look at the source of the energy. Well, it's a great big fusion ball, so we know fusion works, at least on that scale. And that's an X-ray image from the SOHO satellite. So it's, as we know, by far the largest object in the solar system, and actually accounts for, despite the fact that it's light elements, for 99% of the mass. It's phenomenal. Okay, there's a composition, hydrogen and helium. Now this is important from the point of view of solar radiation, because we're interested in what happens in the atmosphere around the sun. That's what's producing the radiation that we see, not what's happening internally. 5,500 degrees Celsius. Now, I'll ask you questions on this later, so remember that figure. And a phenomenal number of megawatts. Okay. So we've already established there's plenty of energy. Okay, it comes from a thermonuclear reaction, where the nuclei of hydrogen combine under very high pressures and temperatures into nuclei of helium, releasing enormous amounts of energy. When the solar radiation arrives at the Earth, it can be converted to heat, and these are solar thermal heaters. So the radiation falls on the surface, and over a broad spectrum, and I'll talk about the spectrum in a moment, but over a broad spectrum it's absorbed. So you need a black surface to absorb, and then water flows through the pipes and is stored in the tank, providing hot water. Okay, and also radiates heat as well. Well, that's heat, but what we really want to do, and that's important, but I'm now not going to talk about that. I'm going to talk about electricity. Because electricity is an energy vector which is obviously very versatile. You know, we can run all sorts of different things on it, off it. And now I'm going to go into a little tutorial. And I'm going to give you some key facts. I know some of you are already experts on this, so I apologize, and you can mark me out of 10 later to see if I've got it right or not. And for those who are not, everything I'm saying is true. So we start with Newton, and Newton was able to establish that light was like waves, and waves have wavelengths, and different wavelengths correspond to different colors. So using a prism, you can actually see the components of solar radiation. Okay, so good so far. So we know that it's composed of a mixture of different wavelengths. But it wasn't until 1901 that Planck explained why the distribution of radiation was the way it was. Now, very often in science, you know, things are measured, you see a particular behavior, but nobody can actually explain it. So this became the big challenge in the late 19th century and the early 20th century. Explain how you get this distribution, this particular shape of curve where, you know, there's relatively little in the ultraviolet, short wavelengths, relatively little in the infrared, but it has quite a tail on it, and it peaks somewhere in the middle. And guess what? That peak in a black body radiator, the best way of thinking of it is a bit of coal in the fire. Well, we don't have coal in fires these days, do we? We have logs or something. But with black body radiation, it has a peak, and that peak relates simply to the temperature. So we're all black body radiators, but we're radiating well into the infrared. We've all seen these police action television programs where the helicopter is flying along with a thermal imager and spots the thief sort of running across the gardens and that sort of thing, and looks like a bright beacon, because that's what we look like in the infrared. Interestingly enough, the early part of my career was looking at materials for making thermal images. And Colin will remember from that time in Morven when we were working on some pioneering technology. But it's all black body radiation, okay? But the sun, we can see it because it's such a high temperature. Remember, the temperature of the sun, 5,500 degrees Celsius, that the peak is right in the visible, so we can see it. You know with a cooker, when it heats up, that it starts to glow red. Okay, so it's the black body radiation. So you've learned about black body radiation. Now, okay, why was Planck so important? He was important because what he said was that when light, which we think of as waves, interacts with matter, it's got to behave like a particle. And those particles we call photons. So okay. So when if we want to convert sun's radiation into electricity, we've got to absorb the light in a surface. Now, we've already looked at the solar thermal heaters, and those obviously converting, absorbing the radiation in a blackened surface. But what we want to do with electricity is we want to release electrons, electric charge, and actually we want that to go into a circuit. So the next bit of sort of theory is from Einstein, and he actually got his Nobel Prize for this, not relativity. And what was observed was that the shorter wavelength light was, the blue, was required to release electrons from a metal in a vacuum. The red, no matter how intense it was, didn't release any electrons. So this gave the idea that the particles of light, the photons, actually have more energy in the blue. And we know that because if we have a sunny day and we go outside and spend too long outside, we get sunburn, and that's damage of the skin from the high energy photons, the ultraviolet. So we're going to use all this to see how we can make solar cells work. This is an example of a silicon solar cell. It's probably a sharp solar cell, so I should acknowledge that. And okay, silicon we know is a semiconductor material, but the particular property we're interested in is that a semiconductor material has a valence band and a conduction band. The valence band is full of electrons, the conduction band normally is empty of electrons, and it's got a gap in between, and electrons can't exist there, and this is an energy scale. In order to absorb light in a semiconductor, you need enough energy to release an electron from the valence band and for it to appear in the conduction band. So half the energy won't do. You need it to be at least as much of that band gap. For that reason, a semiconductor is a good absorber for short wavelength photons, but not for long wavelength. Now, that depends on how big that band gap is. It so happens that for silicon, it's just about the right sort of band gap, as I'll show you in a moment. And as silicon is our most abundant semiconductor material, that's very good news. But there's lots of other semiconductor materials, as I'll explain in a moment. But just releasing an electron is not sufficient to get a current going through a circuit. So the other thing you have to know about semiconductors is that they come in two different types. They can actually conduct with the electrons, or they can conduct with what's left behind, the holes. And to create a current, you've got to get the electrons from one side of the junction, in this case from where it's predominantly holes, across to the n-type side. And there's lots of things that can happen or go wrong, if you like, in the semiconductor material. And if it recombines, then it will just generate heat, and that's not what we want. So there's a lot of things that need to happen. But that is basically a very simple device. That's a diode. It's a diode that's sensitive to light. Now, silicon turns out to be, as I say, not only the most abundant semiconductor, but actually the main source of our solar energy today. And one of the world's largest manufacturing companies is Sharp, and they have their European manufacturing plant just down the road at Fly, and they're this year expanding to 500 megawatts. So that's an absolute phenomenal amount, 0.5 gigawatt of output per year. This shows the modules being manufactured. They're put together from the individual cells. This is a multicrystalline silicon module, and you can also get single crystal as well. Both operating basically the same way, and I'll talk a little bit more about that later. Right, okay, but a module doesn't make the complete system. You know, you've got a pair of wires hanging out the end, and by the way, it produces DC electricity, and we use AC electricity. So you've got to string them together and then connect them into some electronics, which converts that DC into AC, and also does other clever things as well to try and optimize the amount of power that comes out of it. That can be exported to the grid if it's a sunny day and you've turned things off in the house, and you can even get a little bit of money back for that, not a huge amount. Or of course, at night, or if you're using a lot of power, you can import from the grid. So basically, from the user's point of view, you've got electricity all the time, but when you're generating the solar electricity, that is displacing what would essentially be coming from fossil fuels. Because remember, something like 80% of our electricity currently is generated from fossil fuels. So this is the example of what we call grid-connected PV. Now, there are parts of the world that don't have a grid. And for those parts of the world, it might be a kind of a leapfrog technology where they'll get standalone PV charging batteries and that sort of thing, maybe to supply a village or something, because laying in the grid would be too expensive. But in the UK, we have a good grid infrastructure, so we're looking at grid-connected PV. And these are examples of roof-mounted PV. Now, what I'd like you to note is that you can see the different modules fitted together. And you've all seen these. Not maybe a lot of them in the UK, but we've all seen them. We know what they look like. And we see quite a lot of roadside PV modules just supplying, as actually standalone, supplying telephone kiosks and so on, emergency telephones. Why don't we see more PV if the technology is being produced now? It's being produced just down the road by Sharp in ever-increasing quantities, most of which gets exported to Germany, which has a similar latitude to us, so therefore similar amounts of sunshine. Why are we not installing more solar energy? Because remember, the amount that we've got installed right now in the UK is a very, very tiny amount of that quite small renewable energy total electricity generation. Well, the reason is price. Has so many things come down to price. And this is data from a website, Solarbuzz, which kind of looks at all the, analyzes all the data from what's actually being installed and the actual cost that people are paying for it. And the two curves, one is the cost per watt in terms of dollars per watt, and the other one is euros per watt. And they follow similar profiles going from about 2000 to the current time. And the good news is the last 2 years prices have been falling quite steeply. The cost per watt metric is very important because if you think about it, the cost is how much does it cost to produce. You can think about per module or per square meter. And the watt is how much electricity it produces. So we have to worry about the efficiency, but without putting the cost up. And if we can put the cost down by new technology and improve on the efficiency of conversion, then we've got a cost curve which is going to be coming down steeply. And that's basically what's been happening. If we look at the minimum prices, we can see that in fact those are now, for crystalline silicon, I've broken it into two different categories because the multicrystalline is a bit cheaper. That's around about $2 per watt peak. And the lowest thin film now is around about $1 per watt peak. Now 10 years ago, the big target was get down to $1 per watt peak and it's going to be a technology which is going to become competitive. And it is a technology now which is becoming competitive in Southern Europe, but not yet in Northern Europe. So what's happening here is that I just mentioned the feed-in tariff. The UK government last year introduced the feed-in tariff, which is the mechanism which has generated a lot of demand in Germany. And the mechanism in the UK is that if you install PV on the roof of your house, you will be paid something like 40 pence per unit of electricity for every unit that you generate, whether you're using it in your house or it's getting exported. And guess what? Last year, the amount of PV installed in the UK went up by about 5 times, and it was only introduced in April last year. So we've now got that, and we are seeing a growing market. But the potential, we've got to drive down the prices further because we want to get to the point where we don't need any feed-in tariff. We'll all want to go out and buy it because it's going to be the best way of generating electricity, or the cheapest way of generating electricity. And the potential there is with thin film. So what we're seeing is most of the production, and these are predictions from the European Photovoltaic Industry Association, the red bars are the total amount of silicon being produced each year, with predictions going up to 2013. And the green blocks are the thin film. And the thin film is going to, both are increasing, but the thin film is increasing more. And this is because of the prediction of lower prices. So there are things we can draw from that. And now I'm kind of getting into the materials and what we can do in the materials. So thin film covers amorphous silicon, cadmium telluride, copper indium gallium diselenide, CIGS for short, and will be a quarter of the market by 2013. Okay, so it's interesting to look at these market factors and the market drivers, because without that, you know, the technology might work, but people aren't going to go out and buy it. And then materials cost actually becomes a major factor as the production scale increases. And production scale is one of the mechanisms for driving down price. Periodic table. I promised Mark a periodic table. Let's have some chemistry. Well, there's a nice simple rule that you can apply when looking at semiconductor materials, assuming that you know, we know about silicon, we know about germanium perhaps, but there's lots of other semiconductor materials you can make by mixing elements of the periodic table. Some of them are fairly obvious, and the simple rule is that if you look at the semiconductor materials, that's the group 4A, the yellow there. If you form a compound which has an average of group 4, lo and behold, it's likely to be a semiconductor material. Remember, a semiconductor material's got this valence band, conduction band, and the band gap in between, yeah? And with so if we look at an example, that's group 4. Silicon. So if we look at gallium and arsenic, gallium arsenide is a very common semiconductor material now. Probably your mobile phones have got gallium arsenide chips in them. They're also the basis of lasers that are used in optic fiber communications. And, as I'll tell you in a moment, an important part of PV solar energy technology. Cadmium telluride. I've already mentioned cadmium telluride. Well, that's a 2,6 compound, so it gives an average of 4. Let's look at something a bit more complicated. Let's take copper, indium, and selenium. Well, if you mix those together in right proportions, there is a phase, which is copper-indium diselenide. And you can also replace a bit of the indium with gallium to form copper-indium gallium diselenide. And that's now becoming a major PV product. I keep on mentioning PV. Photovoltaic and solar electric are really the same thing. Photovoltaic just meaning we're converting solar radiation into electricity. PV for short. So sorry about the jargon. Okay, there's lots more I could show you, and in fact one of the materials which we're working on, which is very interesting, is iron disulfide. So you can actually go into the transition elements and start to look at compounds, and some of those will form semiconductor materials as well. So the list is absolutely endless. So the ones which we're looking at right now are quite a limited selection of the total. Okay, so a thin film solar cell looks a little bit like this. You could start off with a sheet of glass, and this could be architectural glass, soda lime glass, and then you'd have a thin coating of TCO, that's transparent conducting oxide, because it's got to form one of the electrodes, but it's also got to let light through. So this is where we start to look at the sort of materials properties. If we then add on cadmium sulfide film, that's our N-type semiconductor. Remember, that's one of the things which we need in a solar cell. And then we need an absorber material. Now that needs to have the right band gap to absorb as much solar radiation as possible. And that's cadmium telluride in this particular example. And then we have a back contact. Now a cell can deliver relatively little electricity for a variety of reasons. And any of those steps, as my research team, and the team at Optic will tell you, any of those things can and do go wrong. But we want to get that into high volume production. So just think about the challenge there. It's got to churn through in huge quantities. Okay, so what does it look like? Well, it actually looks a bit different to crystalline silicon. Remember all those crystalline silicon modules? It has a more uniform appearance. These are sort of fairly grey. These are actually produced, these are cadmium telluride modules, and they're produced on the left there by First Solar, which is now the world's largest thin film PV manufacturer. And Worth Solar below manufactures CIGS. First Solar has expanded their production considerably in the last few years and produced in 2009 for the first time over a gigawatt. I think there's a bit of a race going on between First Solar and Sharp, so I won't enter into this argument as to which is the biggest. One is the biggest by revenue and the other is bigger by volume. But it just shows what can happen with a new technology. Now, cadmium telluride manufacturers have been there before, and some have gone out of business. BP Solar actually manufactured cadmium telluride modules and then stopped making cadmium telluride modules and concentrated on silicon. So there's no guarantees that the curve's going to do this. And the way that First Solar have driven down the price is to concentrate on manufacturing technology and go for large volume. So we shouldn't be afraid of doing that in this country. Clearly Sharp are not afraid of doing that in this country. These are examples on the left of where these sort of modules can be used on a huge scale. The largest there is 80 megawatts. This is the peak production in Ontario. So there's some now huge installations occurring. Anyway, somewhat smaller, but nearer to home. And when it was built, Optic Technium actually had the largest thin film PV facade of its type outside of the US. It's an architectural feature of the building, and we're very fortunate that at the time there was a very substantial grant available for demonstrating new PV technology, which meant that we could incorporate it into the building. It's an 80 kilowatt peak system, 85 kilowatt peak, and in its first 12 months it generated 65,000 kilowatt hours or units of electricity, and this is the important bit, a saving of 28 tons of carbon emissions. Okay, so every bit of solar electricity you generate, or renewable electricity, you're displacing the need to generate that electricity from fossil fuels. This is more recent data that we produced ourselves from the facade, so it's still working, I'm glad to say, and this is the kilowatt hours per day averaged for each month of the year. As you can see, the winter months it produces less, but still generates electricity. And one of the things we're interested in are the things we can do to these modules or in designing new modules so that we can actually capture the solar radiation more efficiently in the winter. It actually has different characteristics, spectral characteristics, maybe more diffuse. We have to think about the angle of the sun, etc. So there's a challenge. What are the limits to efficiency of PV cells? Okay, I don't know if you can read that. The optimum efficiency is a compromise, okay? There's always compromises in technology. This is actually a fairly fundamental compromise here. Between the proportion of the solar spectrum that can be absorbed and the amount of energy captured per photon. Remember, we've got to think of light as photons, as particles, when we're absorbing in a semiconductor. Okay, so we've got our familiar Blackbody radiation curve there. The sun behaves as a black body. By the time it gets to the Earth's surface, it looks a bit like the red curve. That's because of absorption bands in the infrared. So we've got infrared to the right, ultraviolet to the left, and a little band showing the visible in the middle. So if you have a semiconductor, so the example there is, don't know what happened there. Go away. I was doing this earlier. Right, okay. So if we look at more for silicon, for example, it's got a band gap of about 1.5 electron volts, and that will absorb in the near infrared, but further out in the infrared it'll just go straight through. Remember, the photon energy isn't enough to excite these electrons into the conduction band, so it just goes straight through. Okay, so that bit we lose. And you say, well, okay, why not have a narrow bandgap semiconductor and absorb it all? Well, you will, but the problem is that the photons, remember, at the ultraviolet end are actually more energetic. And you'll capture just a small amount of that energy per photon. So there's a compromise. And the compromise basically means that there's kind of a magic figure of around about 1.5 electron volts for the bandgap. Now, see what's in there. Silicon, crystalline silicon over to the left-hand side. Gallium arsenide I mentioned. On the right-hand side, it's cadmium telluride is in there. And these are all semiconductor materials which can generate something like 30%. Now, we don't get anything like that. Now, I haven't talked about efficiencies up to now. I've talked about total amounts of solar radiation and what's available. And then the question is, how much can we capture? Well, with a single junction cell, you won't do better than 30%. Are there ways of doing better than that? Well, yes, there are. And one way of doing it is actually to have multi-junction cells, and the structure shown on the left-hand side there. And it's based on germanium substrate. It's got indium gallium arsenide in there, indium gallium phosphide. And it's actually 3 junctions built together. And as you can imagine, this is a very complex structure. It's not easy to make. It has to be made very high crystalline quality. And guess what? It's not cheap. But what it does is it gives you much better capture of the solar spectrum, because now each little bit can be captured more efficiently. So the blue, the green, and the purple basically show how these different cells can capture different parts of the spectrum. And the best now is up to over 40%. Okay. This is a chart which is produced by the National Renewable Energy Laboratories in the US, and basically puts every sort of technology on there. And why do NREL produce this chart? Well, if you look at a lot of the world records, they've come from NREL. So when we're producing a few world records, Vice Chancellor, we'll be producing our own chart. The best up there, of course, is the triple junction, is also the most expensive. Crystalline silicon is the blue open squares there. Each of the technologies seems to saturate, doesn't it? You know, we'd reach a point where it doesn't improve very much. Cadmium telluride, one which we're working on, hasn't improved since about 2000. And it's about 16.5% efficient. Only about half of what we could actually produce from it. If we look at some of those down the bottom, well, why bother with those? Well, that's actually based on polymer materials, plastics, polymer semiconductors. And there's also above there dye-sensitized solar cells. So there's many different ways you can make solar cells. Now, why those are interesting is they can be made very cheaply. The efficiencies are low right now, but if you can get the efficiencies up for those, you've got inherently cheap technology. So this is a nice chart to show, because this is basically all the technologies, and there's a lot of information there. Okay, so cost-performance trade-offs. I'll go through this fairly quickly. So the highest performance solar cells, the triple junction solar cells, based on gallium arsenide, they're too expensive for building an integrated PV, but can be used, and as the whole purpose has been for powering satellites, where they need a lot of power, and they can stand the cost. There is an application for terrestrial application of triple junction solar cells I'll mention in a moment. Very low-cost dye-sensitized solar cells may be suitable for large areas, such as industrial roofs. And again, we've got something in Wales, just down the road. There is actually a pilot plant at the Tata Shotton factory, collaboration between Tata and Dysol, where they're actually looking at coating dye-sensitized solar cells onto steel sheet for roofs. Low efficiency, but low cost in large areas. So you generate reasonable amounts of electricity. Crystalline silicon is our mainstay, and that produces between 15 and 20% efficiency at the module level. In the laboratory, it's up to about 24, 25%. So that's actually doing pretty well. Thin film silicon and all the others, well, they've still got a way to go. Concentrators. This is where you can use the expensive cells, because what you're doing is to concentrate the light. And this is actually 2 British companies start-up companies which have set up to manufacture complete systems which will scan the sun. So it's not something you put on the roof of your house, but you could have a large array of these. And the one on the left uses trough concentrators, reflectors, and the one on the right uses plastic Fresnel lenses. And one of the facilities at Optic Glyndŵr is actually producing the drums that can manufacture these plastic lenses. They have to be very cheap. So that's an exciting area, and the cost projection for this is actually looking very attractive. You can concentrate up to 1,000 times. Certainly 500 times is readily achievable. And these things still work. And these are amazing devices because they're going to run pretty hot. Okay, so the opportunity for the UK to generate substantial amounts of solar electricity is by incorporating the fabric of the building. So we probably won't be using too many of those concentrators in the UK, certainly not on our houses. So we've got thin film. That's got cost advantages, but we've got to get higher efficiencies. We've got to get up to those regions that crystalline silicon enjoy. Thin film can be either on rigid surfaces such as glass or on flexible surfaces. And there's an exciting possibility, steel or plastics. Opportunity for designing or even disguising PV in buildings. So there's enormous architectural opportunity. So I now want to give you some examples. I'm kind of giving you too many words, really. This again is a British company, Polysolar. They've just gone into manufacture thin film silicon that's very thin film and actually lets some of the light through. Now very often, glazing in buildings, we have to put a coating on so that it doesn't get too hot inside. You can make that into a solar cell if you use thin film silicon. And it still produces quite a lot of electricity. So this is just going into production. It probably is about 8% efficient. Looks very attractive. The one on the left is actually a large greenhouse and will help with the thermal management as well as generating electricity. Solar tiles, if you want to disguise on the roof of your house. Another British company, Solar Century. This actually uses crystalline silicon. They can be made from thin films as well. Solar facades. This is examples from Green Coast Solar. So again, you can put them onto the walls of the building, into the glazing of the building in a way which doesn't even look like PV, but is generating electricity. So what do we know from our current knowledge of materials science, what can be improved on these solar energy materials? Okay, we need to improve the light capture. If it reflects, we're losing energy. And if you look at a PV module and you look at it at an angle with the light, so that might be with the sun low in the sky, it tends to reflect. The facade at Optic does. I mean, it produces some quite nice photographs, but when I look at that, I think, you know, that's some loss in energy. So we want to think of the whole light capture as an important part of the equation. We need to work with a wider range of materials to integrate PV into buildings. We need to improve the efficiency of low-cost PV, such as thin film and organic. And photon management, this is a wonderful word. It was created by some colleagues on the SuperGem project at Southampton University, and I'll show you some results on that in a moment. But this is, we're trying to capture more of the solar spectrum than we are right now with single junction cells. And building extra junctions in is expensive, so this is a way of being able to deliver the photons at the right sort of energy for the semiconductor. And hybrid solar cells, if we can do it cheaply. Okay, crystalline silicon cells. Silicon actually is quite a highly reflective material. So you can lose a lot of light from the surface before it's even got into the material itself. So there's ways now of being able to texture these surfaces, and these are SEM images of silicon cells, which show by texturing the surface, they actually look much blacker than they used to. And something looks black, it's absorbing solar radiation. These are our laboratories in Optic. We've got fantastic facilities. We can deposit the materials, all stages of thin film PV manufacture, going through all the way to making some test cells, and bottom right there is the solar simulator where we actually test the performance of the devices. We're looking at some developments of research of thin film deposition technology, because remember, it's about manufacturing and how do we actually get the films down in a way which can be both control the properties so we can get high efficiency, can be low cost, and is also compatible with high volume manufacture. Well, we started out taking a fairly sort of conventional approach where we have a batch process. This is using metal organics as a chemical precursor to react onto a hot surface, and the little schematic on the left there shows the gases sort of flowing, and this will all be enclosed in a cell. You'll be glad to hear, because some of these are very toxic materials, and is all nicely enclosed in a cell, but basically just flowing over the surface. Now, this is not compatible with a high volume process, which basically is a production line moving along. It's a bit like putting things in the oven and sort of taking it out an hour or two later. It won't work. So we've built a system which injects the chemicals down vertically, and the substrate now slides underneath. And that's working very well. But we're not going to stop there. We're already building the next system, and this is under the SPARK project, which is a consortium in Wales, part of the Lowcarbon Research Institute. And what will happen here is we'll have different injectors. The substrate will move underneath the injectors, coating on these different layers that are needed in the thin film structure as it goes along. So that's the cadmium sulfide, that's the window layer. Cadmium telluride, it's the absorber layer. And we have a little trick at the end there, just to try and make the contact. And then there's what I call a little bit of alchemy. That's because, as I'll show you in a moment, hopefully, these materials look horrible. And for anybody who's worked on semiconductor materials and made semiconductor devices such as lasers and amplifiers and all sorts of different things, high-frequency amplifiers, you won't have material looking like this. It'll look like the schematic that I showed you earlier, with nice smooth layers, all well-defined thicknesses. If you deposit materials onto glass, this is what it looks like. And we need to use glass or metals because we've got to keep the cost down. So what we've actually got is lots of little crystals there. So on the left, we're just looking at a plan view. This is what it looks like in an electron microscope. Very small grains of crystals. On the right, this is taking a cross-section through it. The interface here is with the glass. The cadmium the TCO you can barely see. It's very thin. The cadmium sulfide is also very thin. You can just about see it. Most of that is cadmium telluride. Just imagine what would happen if there was some sort of gaps between those grains of material. What would happen when you put a contact on the back? Well, we don't have to imagine, we can look at it. So one of the research students, Will Brooks, has developed a technique where he scans a laser across the surface of this is a device, looking at a complete device, and 3 different wavelengths, looking at blue, red, and infrared. Now it so happens the blue will absorb in the cadmium sulfide layer, so it shouldn't actually get through to the cadmium telluride, but the peaks there show that in places it is. And we've gone on to show that this is because in those regions, that window layer is actually very thin. And you might wonder, well, what effect does that have? Because, hey, it's letting a bit of the blue light through, isn't that good? Because that's one of the problems with cadmium telluride cells. They're not very good in the blue. Well, you can see that in exactly those regions, in the red and the infrared, where the light does get through to the cadmium telluride, the performance is poor. So this really tells you that it's no good just saying, you know, I've managed to mine out a really good piece of material and get a good device on it, because this now has got to be manufactured on a large scale. And so you can see the challenges. Materials uniformity is everything. Just decided to, oh, there we are. Okay, no, I want to go back now. Right, okay. I mentioned, I just want to show you very quickly another example of where we're using innovation to try and improve the efficiency. This is a quantum efficiency curve. I'll try to take as many graphs out as possible, but this is one I really wanted to keep in there. You look at the wavelength scale. Red is around about 600 nanometers. 900 is into the infrared. That's the band gap of the cadmium telluride, so all the longer wavelengths go straight through. The blue doesn't pick up very well, so this is the quantum efficiency curve here. It's not very good because of the absorption in the cadmium sulfide. At Southampton University, in a collaborative project we've worked on together, they've taken our cells, they've put dyes into a polymer, and these polymers fluoresce and re-emit the light in the red, which will get through the cadmium sulfide and be absorbed in the cadmium telluride. So that's what the green line shows you, that we're actually getting some response there. In fact, they got up to 80% efficiency in that region, which is very impressive. But not to be satisfied with that, one of our research students, Simon Hodgson, is working on using nanomaterials to do the same thing. And these are some early examples. You can see on the left, well, it's just a polymer film. It's colorless, can't see it. And then we've put the nanomaterials in, and you can see it's nice and orange. It is actually absorbing in the blue. That's what it's supposed to do. If we shine a blue laser on, the polymer film doesn't do anything, just glows blue. But if you look at the nanomaterial, we've actually got red fluorescence. And of course, the red will get through that cadmium sulfide. So kind of gone through some technical details there. But what I want to do is give you the flavor that with sort of technical, you look at the problems, and then with technical innovation, you can actually come up with low-cost solutions that can improve the efficiency of these cells. And remember, if we improve the efficiency and we don't put the cost up, the cost per watt peak comes down. Right, so now to my conclusions. So I'm taking you on a bit of a journey from the Pacific Ocean to some rather sort of technical details and bits of history of science, where science of the 20th century really informs what we do today. There's certain key bits of science which we've got to remember when we're working on this. So solar energy has enormous potential. It's there every day, but we've got to get cleverer about improving, about the capture of the solar radiation. So we want to capture more of the solar spectrum. That's one way of doing it, but it can be challenging and it can be expensive. Solar electric modules in the future will become part of the fabric of the building. So what we're going to see is buildings which architecturally are functional, architecturally hopefully look attractive, and the PV will be built into the fabric of that building. It won't be, here's the PV, we bolt it on. That's the challenge, and that's a materials challenge. Materials innovation is needed at all levels of PV module manufacture to improve the efficiency and reduce cost. And although I've talked a lot about thin film, there's a lot of innovation and so on that's going in with crystalline silicon. These things are improving all the time. We'll be able to reduce our carbon emissions. Well, will we be able to reduce our carbon emissions in time? To meet these targets, to keep our global temperature within 2 degrees. That's a question I leave with you. And also, I leave you with another question. What will the climatic conditions be in 2050? That's only 39 years' time. Sounds quite a lot, but it's not a long way off. What climatic conditions will we have? Will we have succeeded in displacing fossil fuels? Will we be using our energy more efficiently? So I leave you with those thoughts. I want to acknowledge, obviously, members of the CESA team. I get to give the talks, they get to do the work, and I've got a fantastic team there and grown quite considerably since we joined Glyndŵr University. Pilkington, one of our partners, supplied some commercial glass which we've been using. Financial support from the EPSRC and also from the Low Carbon Research Institute and you can see the various logos there, and names of the CESA team. All right, as shown, I hope I've included everybody. And thank you all very much for listening.
Stuart, a terrific lecture tonight, and you made it sound simple to understand, even for a Shakespearean like myself. And I'll try and weave it into a Shakespearean lecture somehow. I promise you that.
I look forward to it.
Yeah, I know. You're keeping to it. I don't know how I'll do it, but I'll do it. But you now take some questions.
Yes, certainly.
Does texturing the silicon?
Oh, can you just wait a moment for the microphone?
Yes, it's texturing the silicon means that it retains particles from the atmosphere. Does it degrade fairly quickly?
No, the silicon is actually encapsulated. So the process that's carried on at Sharp actually completely encapsulates that. But we are interested in texturing the glass. And if you think about a PV facade, we don't want it to get dirty. Now, one of the great things about our climate is that the rain regularly washes it. So the PV facade at Optic, we have not had to do anything to clean it. We would actually like to texture that more, but then the question is, how do we do that and not retain particles? So the first part of your question about the silicon, that's already established because it's encapsulated. But the implication as regards the surface of the glass, we don't have an answer to it yet.
Stuart, thank you for an excellent lecture. Question, what more can be done here in Wales to take all of this forward?
More research money, of course. I think that one of the challenges we face is taking new ideas into production. It's something we're often criticised for in the UK. You know, we have good ideas, they go abroad. I gave a talk in Bristol last night, and one of the questions said, we don't have a manufacturing industry anymore in this country, and I can't remember what the rest of the question was because I said, yes, we do. We certainly do. But how do we connect between the two, and how do we do it in Wales? I think in Wales we're in a very strong position because we've actually got a lot of the UK's PV industry in Wales. We've got a lot of the supply chain in Wales. We have a culture in Wales which says that manufacturing is alive and well, and we're proud of it. And that's got to be a good starting point. And we've got to believe in manufacturing technology. We're not going to ship out all the manufacturing to China. China will be supplying a lot of its own needs, and it makes a lot of sense to manufacture products close to market. And the world's biggest market for PV, solar electric at present, is Europe. So I think there's a lot we can do in Wales if we can start to make those connections.
Thanks. I've spoken down on these before. Stuart, I was given to understand, I'm not an electrical engineer, but to me the prime mover should be constant. We don't really achieve that in this country, do we? In sunny air climes, maybe. We could achieve it with our river systems, couldn't we? Even with a simple water wheel.
No, I mean, if you think of the demand of electricity, that's not constant, but we manage the grid to satisfy a rapidly changing demand. By the time we get the kind of penetrations into the grid from renewables, yes, which do change according to climatic conditions and during the day, by the time we get those sort of penetrations, we will have the means to manage that. The way to look at it isn't what is being produced at each second during the day, although that's important, but what's the total amount of electricity? The total amount of electricity that we could generate from the sun in the UK could all be used, and by using it, you would not then be generating electricity from fossil fuels.
No, I don't dispute that, but what I am saying is this. Our climate is not constant for a start, and with electrical energy, the prime mover needs to be constant. That's what I'm saying. With the simple water wheel on our river systems, we can achieve that. I'm not saying we shouldn't use this, but it's more suitable for sunnier climes. Africa, for instance,
No, I mean,
sun shines all day.
No, sunnier climes. If you look at that curve that I showed,
Well, I don't know. It seems complex. You know, what you've explained there seems very complex to achieve.
It's still going to vary. I mean, you get more energy in sunnier climes, but there's still more than enough energy that's available within the UK. We've just got to get clever at capturing it.
I still think we should be moving to the water wheel on the river systems. Thanks.
Well, I think that the message that I really want to give is that we can't just pick on particular solutions, because particular solutions will not produce anything like enough energy. So we've got to solve the problem so we can actually use a combination of solutions.
Stuart, it's a long time since I asked you a question. Can I just say how much I agree with your comments about climate change, though, and that also that we have to move away from fossil fuel, particularly oil, because it's peaking just about now, and by 2030 it's pretty much all gone. So we don't have long, really. And I think what you talked about tonight and other options such as wind and tidal and so on, and water and rivers. I mean, as you say, there's no one solution. But what I wonder what you would say about the need to store energy, because, I mean, we're going to move to an electric-based economy, no question about that. But the thing you can do very easily with electricity is store it. Yes. So perhaps would you like to see how you would integrate solar and all these other erratic, to some extent, energy sources to get over this problem of evening out the demand, you know, the peaks and troughs in terms of supply and demand?
Yes, Rex, I'm glad you asked me that question.
I wasn't put up on that.
I realised one thing that I didn't say when I talked about renewable energy. I didn't talk about renewable energy vectors. Okay, so we are looking at a very complex equation here. We need to look at storage, of course. And I think one of the most exciting ways in which we can store, if you like, surplus electricity produced in any particular time of the day or the year is with hydrogen. Now, it's very interesting. A lot of the focus on hydrogen has been storage materials for transport. Yeah. And we always take the toughest technology. But as you've shown with the hydrogen barge, it's actually an advantage having a fairly heavy storage medium to safely store hydrogen and to have a very efficient and clean and I gather silent means of transport. So not saying we're all going to go around in barges in the future, but it's a way of being able to store it over long periods of time. Of course, with fuel cell technology, Rolls-Royce are doing a lot of work on solid oxide fuel cells, which simply would be for generating large amounts of electricity, which could go back into the grid if we've got the hydrogen, which comes from a renewable source.
Thank you very much, Stuart.
Thank you very much. Really good to be here, Stuart. A really excellent lecture. Well done. Just for a change, I'm not going to get into details semiconductor physics as we've done over many years, but can I come back to this slide that you showed about interfacing with the... Sorry, I'm trying to hold this a long distance away, but interfacing with the grid. Sorry, no need to dial it up. It was a nice, very clear slide. But in the repeated other circles in which I move, that keeps coming up time and time again as being an area where there are key technical issues still to be resolved. Yes. You seem to indicate that it had been solved. So which is the true story? Well,
some of it's been solved and some of it hasn't been solved. What has been solved is you can go out and buy it now, you can install it and it'll work. And it'll actually produce the amount of electricity that is predicted for any particular site. What hasn't been solved is the long-term reliability. The PV modules themselves have given a sort of a guarantee for 25 years. For some of the newer materials, it's very difficult to be able to test them and to be confident that they're actually going to operate for that length of time. So that is a materials challenge that I don't have any answers to, but we are setting up facilities so we can at least do some of these tests and understand what the failure mechanisms are. And the other bit that is probably the most unreliable part of the system right now, the most reliable part is actually probably the PV module, is the power electronics. And the mean time to failure for that is something like 5 to 10 years. And you've just gone out and invested your money in a system which you want to operate for 25 years because that's what the calculations show that you need to operate it to get the money back. So we either make it a heck of a lot cheaper and we write it off in 10 years, or we make it a lot more reliable.
Last one. Last question.
In your lecture, you mentioned the periodic table and the semi-metals that you've chosen to make up the cells. In today's advanced electronics, we find polymer and plastic organic materials. I believe that Germany has put a patent in for something which, a material that will actually generate electricity from photovoltaic sources. Do you know of any future for these?
Or from the polymer side?
From polymer side, not using the semi-metals used today.
It is possible. In fact, it's one area where the UK is very strong, and there's many different ways of doing it. The efficiencies tend to be quite low at present, and these are laboratory efficiencies. There's nothing out there which is in production, so this is small scale, not large scale, but potentially could be large scale. The one bit of the organic picture which is in production now is the dye-sensitized solar cells, which is really a sort of a hybrid with nanoporous titania.
I did wonder if it was.
And that now is in large-scale manufacture, again in Wales, in South Wales, with G24I. And but they're producing not PV to go on the roofs of houses, but for consumer products.
Like radios or some, like radio sets or some sort of thing.
Well,
like
yes.
windowsill.
Wireless keyboards and so on. So that's just emerging. But in the future, I'm sure they will be manufacturing them. And of course, the great thing, it's onto plastic. So think what you could do with that.
Yes. Thank you.